All right, thank you, ladies and gentlemen. Oh no, it's still a few more minutes, so let me just wait until 20 past on the dot. I will... If you do have any questions, please ask them in the chat. And we'll just give everyone a few more minutes to arrive. All right, thank you. All right, so I've got 20 past, so let's begin. So we're going to begin with an overview of the work that we covered previously in 1B, but we're going to quickly talk about the things we covered and then focus on the limitations of the techniques that we used up to the point Computer Science 1A ended, and what we can do to maybe improve upon those limitations using what we know so far. And we'll see that this approach doesn't really work perfectly. And then we'll see what C++ introduced to the original C programming language to allow this other style of programming to be much more simple and straightforward and integrated into the language. So a large chunk of this course is going to focus on computer science, on object-oriented programming, but the actual purpose is the creation of our own data structures that are able to contain both the data and behavior in a single unit so that you can't use them inappropriately. And we'll see that it is possible to design programs in this way without using object orientation, but we'll see that the tools that object orientation bring does make this a very natural way about going about things. Also, let me just mention some bookkeeping things. We'll obviously be doing Friday practicals as before. Everything is going to be online this semester. So please note that there will be a practical on Friday where you'll be given an assignment due the following week, and then you can ask questions about that assignment and everything. There's nothing due this Friday, but on Friday you'll be given your first assignment. So please don't forget about that. All right, so I won't dwell too long on things like the numeracy and so on, except as they relate to what we're trying to achieve here, and there is some overlap. Our initial work will focus quite heavily on the use of pointers and dynamically allocated memory, and particularly the link between pointers and functions, which is not something we focused too much on, although we did have some slides on it and it was sort of additional extra information. And then we'll look at how we can extend the types that already exist in C++, and we've already learned how to do that with enumerations and structures. And then we will move further in extending the type system in a much more robust way. All right, so let's begin. So how could we extend the type system? Well, the easiest thing to do is to just rename an existing type that already exists. And we did that with type definitions. So remember, a type definition just creates an alias or an alternative name for a type that already exists. And we used it quite heavily to make working with arrays much more straightforward, because you don't want to be mucking around with pointers the whole time. You'd rather think about your array as its own data type. So, for example, we could create a type definition for int pointer to refer to an integer array type that now exists, and then we can use integer array as a type wherever we would use int pointer. Once your program compiles it, it boils down to the same thing anyway. This is just to make it easier for you as a programmer to see what you're doing, and then you can pretend integer array is a existing type, allocate space, and so on and so forth. Likewise, and we didn't spend too much time on this in the first semester, a function or your code all gets compiled. We know that. And it gets compiled into binary values that then get loaded into memory. So somewhere in memory when your program is running is the binary representation for the instructions for your functions. So sometimes you might want to get the memory address of one of those functions so that you can use the data or store the function as if it were data, or at least the address of the function. So we could create a type definition for all void functions, for example, because a void function's type would be void, and then whatever we're going to call the function pointer type wrapped up in parentheses with a star in front of it. And this one takes no parameters, so open parenthesis, close parenthesis. And if we wanted to create a reusable type, rather than have to write this messy sequence of characters every single time we wanted to work with the void function pointer, we could create a void function type using a type definition and then use that from that point onwards, rather than type this whole thing out every single time. And sometimes when you're programming, you're not quite sure how much space you want to allocate for, let's say, your numerical types. So if your numbers are very, very small and you want your program to not take up that much memory, and you know for a fact, for example, that your numbers are only going to be, let's say, between 0 and 255 in range, then you could use a short, for example, to represent them. But maybe you want them to be a slightly larger type, you might use integers. Let's say you wanted more values, but you knew they'd never be negative, you might want unsigned integers. And let's say you're not really sure, and it might change in the future. You don't want to then have to, at some future point, hunt through your program and change every place where you used a short to be an integer, or an unsigned integer to be an integer, or vice versa. Or even between doubles and integers, if suddenly you realized you might need a fractional component. So one other use of type definitions is to create your own type alias, so that you can, with one edit, change one line of code once, and then recompile your program and switch from integers to shorts to doubles to whatever you wanted it to be. So that's another very common use of type of. But important thing to note here is we haven't at this point in time actually introduced a new data type at all. We've just created a new name for an existing type. And even when we did create our own new types, for example, with structures and enumerations, there is a difference between a type that a programmer creates and a really good and useful data type. So our goal this semester is we're going to focus on trying to create what we call abstract data types. So all programming types we create, be they enumerations or structures or some of the more advanced ones we'll look at this semester, the classes and so on, that doesn't mean that they're very useful. It just means that a programmer has defined them. So you, the programmer, introduced them. It's a programmer-defined type. But if you've done them in a very careful way, where the logical properties of the type are kept separate from the implementation details of that type, we call it an abstract data type. And that's a very good goal to aim for, because an abstract data type means you can change how the type works as long as you don't change the logical properties. You can update the type, and no one who uses it will have programs that suddenly break. So say, for example, they made a vector that was far more efficient in the future and used less memory and ran faster and was just better. They could change the definition or the implementation of the vector type, and everyone who's using it might suddenly notice their programs are running a lot better, but nothing that was existing before would stop working correctly afterwards, because they kept it as an abstract data type. The logical properties, how you use a vector, is different from actually how does the vector work under the hood. So that's our goal in this semester, is to be creating abstract data types of our own. So the first way in which we created effectively a new type, I mean, type defs are aliases, and creating an array of a particular size is grouping together a bunch of pre-existing types, and using an enumeration is like creating a bunch of constant integers. But the first time we really created our own types was where we grouped a bunch of different values of different types into a single named entity. And that was through the use of the structure. And that's where we're going to start our exploration of more sophisticated programming in this semester. So we've seen this already. Structure groups related data, they're related conceptually, but their types could be very different into a single unit. So for example, all the information related to the game was grouped, for example, into a game world structure, or maybe the you could have the player as a structure where the player's row, column, and what they're holding is stored in its own structure, or whatever you want. The way you split up a problem is part of the art and science of computer programming. So that can vary depending on you, the needs of your program, and so on and so forth. But anyway, the structure itself just groups these related types together. And as we know, also the individual types in a structure could be structures themselves. So you could nest structures within structures within structures, or have arrays of structures inside a structure, and so on and so forth. So how big is a structure in memory? Well, at minimum, it needs to be as big as each of the types added together, each of the variables added together, because each one can be stored simultaneously. So that's the smallest size a structure can be in memory. As we'll see this semester in practice, they can actually be a lot larger. They can be as big as, additional empty space can be added at the beginning and the end of the record structure, sometimes even between elements within the record structure, just so that the total amount of size of the structure is a nice unit for the operating system to work with, which will become significant when we start to take structures in memory and write them to the hard disk and read them back from the hard disk. So that's an important thing to note. The size of, there's a keyword size of in C++, which will tell you how big something is in memory, is at minimum going to be the size of the types added up, but can be much larger. And another thing we'll also have to look out for is arrays. If the array is just a pointer. This is a wonderful question that you ask me. So someone has just asked, can a structure contain itself recursively? And the answer is absolutely yes, and it's wonderful. And we will be doing that this semester when we create node-based data structures, where a node can contain other nodes that can contain other nodes off to infinity. Well, not literally off to infinity, but with no hard-coded limits. So we use that trick to create things like tree structures and graph structures and linked lists and so on and so forth. So you'll use it in this semester, you'll be introduced to it for the first time, and pretty much the entire focus of Computer Science 3A is the kinds of data structures you can create using that trick. So that's a wonderful question, thank you. So anyway, here is a student structure that stores a string with the name of the student and their student number, and very rarely you can, when you define a structure, introduce variables of that type straight away. We don't do that almost ever, because remember, we like to put our type definitions inside the header file, and variables should never go in the header file. And basically by doing this, you've created a variable of type student called Bob, a variable of type student called Tandi, and a variable of type student called Suresh. So that is not something you'd put in your header file. So you'll very rarely see this, but we do remind you that it is possible to do that. And then, as we've seen before, sometimes we want to reach inside a structure to get hold of the variables that are inside it, the fields of the record structure, it's sometimes called, or the elements of the structure. The correct name are the data members of the structure from C++'s point of view. So the name of the operator is called the member access operator, or very commonly just called the dot operator, because it literally is the period, the dot. So if we created a student called Linus, we could access the name data member by saying linus.name and set it to some value. Likewise, we could set the student number through the dot operator and set it to some value, and we could access them each one at a time by saying the structure dot data member, structure dot data member, and so on and so forth. A very useful trick, to be perfectly honest, with structures, which actually isn't done all that often anymore. But the original C language and C++, because it inherits from it, didn't have any support for returning arrays from functions as a return value. So we got around that by switching over to dynamic arrays very quickly and simply returning a pointer to the free store allocated contents of that dynamic array, and then we were quite happy. But you can return structures from functions, and structures can contain fixed length arrays. So a common trick, if you're ever working in a very constrained environment where you can't use, for example, there isn't much heap memory, much free store memory available, and you have to work on the stack, which can be the case in some embedded systems, or if you're working on a very minimal subset of C++, which can happen. Sometimes some employers restrict your use of advanced features to keep the code simple and maintainable, but you want to return a fixed length array and you can't, and you're not allowed to use, let's say, for example, the C++11 array data type, which you can, in that case, return from a function. You have to use the built-in arrays then, and not the modern C++ ones. You can then do this trick where you put your fixed length array inside a structure and then return the structure, and then you can access each of the elements one at a time quite nicely. It works very, very well. So, and then off to this point, we won't do the recursive hierarchical structures yet, but we will in a later on in this course. But the straightforward way of defining them is you define the structure that you want, and then another structure afterwards, which has the first structure as one of its data member types. So here we've separated out the biographical details from the person. So that the person has a name, an age, and a gender, and then instead of that we can have the biographical structure as a data member of a person called details. Let's say this is obviously an access control system because there's a reason for visiting string. And then we could say, let's say we have a person Bob, so bob.details.name equals Bob, or .age or .gender. I guess I should probably modernize this because a binary gender classification is actually not appropriate anymore. So you should really have a string or character-based gender system these days so that you can accommodate many types. So that is something worth thinking about. I should update those slides. So let's move on. Oh, actually, sorry, let me move back. Let's actually just show you there is another way of doing this composition of types with structures, which is not structures, which is, we tend not to do it in our style, but there's nothing wrong with it, and it does happen. So let me just quickly whip up an example for you. You can actually define the structures nested inside each other, and they sometimes call those nested structures, and some people really like that style. And it is more common in other programming languages. C++, I can't really say that it's not common either. It's really much a personal style thing. We'll accept whatever you want. I'm just going to make a simple C++ source file. This stuff would normally go in a header file, but there's no need to make a whole project for this. A nested structure. Just put it on the desktop. It's just a quick throwaway. So let's say, for example, we had a structure that represents the person, like before. Let's say that the person had a name. And then let's say we wanted to have their biographical details. What you could do instead is go struct biographical details and define it right then and there as a nested structure. We tend not to do that. We prefer to keep them separated out because it's less complicated in a sense. But some people really do like to nest their structures this way. If you do go ahead that route, so we're definitely not going to penalize you in any way. It's just our personal style, or at least my personal style doesn't use it that much. But up to you. Same effect at the end of the day. All right, so let's move on to another data type, which we could have covered last semester, but it's actually very rarely used these days. There is a better C++, modern C++ version of it that's coming in with 20, I think, C++ 20. Anyway, it's called a union, and its job is to give you the option of one of multiple possible values of different types. So maybe you're storing a value that could be an integer or a double or a Boolean under various different circumstances, and so you only want to store one of these values at a time, but you don't want to like store extra memory to have a structure where they will all be there, but only one of them is actually in use. So you want to basically minimize the amount of memory you use based on the fact that you're only storing one value of a particular type in that space at a time. And the data type for that is called a union. They look very suspiciously like a structure, but their purpose is very different. So basically what happens here is that each of the data members of a union aren't stored at the same time. Basically, the largest one, the largest type from the set here is chosen, and enough space is allocated only for the largest one. And then basically the memory is used for whatever value you're storing in it at that time. So let's say you've got a short, an integer, and a long. Obviously, the long is much bigger than the integer, which is much bigger than the short. Then your unions type, if you join them all together, would be as big, minimum as big as the size of a long. And then you'd have to specify which way you're interpreting that data by the data member that you access. So let's show you an example. This is actually one very rare example of when it's a good idea to use a union. So I'm not sure how much you know about data communications and networking, but you will do, if you carry on with computer science 2B is focused very heavily on networking and data communications, as well as writing programs that can be distributed across a network and cooperate and so on and so forth. But the fundamental way in which our computers on most networks communicate is via a protocol called IP, the Internet Protocol. So a protocol is basically the rules by which a computer or systems will communicate with each other. And IP powers, unsurprisingly, the Internet. And still the most common version of IP is something called IP version 4. And basically every computer that's on the network gets assigned at least one IP address, which is basically their name, basically a number that represents them on the network so that they can communicate with each other by that number. So it's a big number. It's a 32-bit number, so 32 ones and zeros. But it's typically split up into different chunks. And one of the most common way to split it up is to split it up into 4 sections. And some of those sections will represent the name of the number of the network, and some of those sections will represent the number of the computer on that network. But it's still one number. It's just easy sometimes to think of it as 4 numbers between 0 and 255 rather than one giant 32-bit number. So this structure will, this union will let you do that. You could store the number just as a 32-bit number straight, or you could store it as an array of shorts. So in this case, the assumption is that a long is 4 times as big as a short, which is often true. And then you can access each of those numbers one at a time. Okay, we've got another question. Do unions do the same thing as a template? And the answer is no. We will study generic programming or templating this semester as well. Templating gives you the ability to create a reusable data type that can work with a lot of underlying different data types that you specify. And a perfect example of one that you've all used is a vector. What is a vector? It's a container. A container of what? It could be a container of integers, a container of booleans, a container of student records, who knows? So the mechanism by which that is created is called templating, and the style of programming is called generic programming, and we will do that this semester. Unions are much more primitive than that. They're basically what we call a variant data type, a limited type variant, and all that happens is when you call this by sections or when you call this by number, that tells C++ to interpret the memory as either a long or a short, depending on how you accessed it. So if you store, let's say, one that's got a double and a character and a boolean in it, and you put a double in, and then you read the boolean out as a character, you're not going to get any error message. It's just going to give you gibberish. Whereas templating will actually create a new version of that type that's specific for booleans, and you can't then try and put a real in it. It will just, the compiler won't let you. So generics are much more sophisticated. But Eugens do exist, and they're worth pointing out to you. We won't really require you to use them for anything, but we do want to give you the full picture of what's going on. So one of the techniques we're going to use to create these abstract data types is called object-oriented programming. And object-oriented programming is not the only way that you can create abstract data types, and it's not the only way to program. During the late 90s and early 2000s, it was the way of programming. And pretty much all programming languages that came out during that time, there's things like C# and Java, were all very object-oriented. Even languages that were more focused on things like scripting, like Python, you can create in an object-oriented style. And lots of programming languages have support for object-oriented programming. It is incredibly useful. But I think we went through a phase where people went a bit crazy with object orientation as well. And it's not the best way of programming for every situation. If nothing else, I'd like you to think about programming as building up a toolbox. And every new language you learn, and every new library you learn, and every new technique you learn is just one more tool in that toolbox. So while a screwdriver is very useful for removing screws, it's not terribly useful if you need, for example, to hammer nails into a wall. Technically, you could hammer nails into a wall with a screwdriver, but you can have a very bad time. So object orientation is very powerful and very useful, and we'll discuss why it's powerful and useful, but it's not perfect. So a lot of people think once they've learned object orientation, they basically stop learning and don't learn new programming styles. And I would really suggest you keep learning. One of the other very important programming styles that's become more important in modern programming is something called functional programming, which doesn't just mean programming with functions. It means programming in a mathematical style that uses functions in the mathematical sense, not just in the computer science sense. And there is a difference. That's become very more widely used, let's say, in the 2010s and now still in the 2020s. So there's always something new to learn. So let me just, before we start on the object-oriented journey, let me just mention that it's not the final destination. That'll be up today. I just needed to check when the due dates were for some of the applications, but that'll come up probably a few minutes after I've done here, or at least definitely today. That'll be up. It actually was up temporarily, and I had to remove it when I realized I didn't know what those dates were, so I didn't want to confuse anyone. All right. Okay, so there are many different techniques and principles of object orientation. And that's probably also part of what can make it confusing. It's a lot of different things that sort of are used together collectively. But three very important techniques that exist in object orientation are encapsulation, inheritance, and polymorphism. These two are often used together, inheritance and polymorphism. So encapsulation is the ability for us to basically combine all of the data and all of the behavior that is sort of necessary for an entity into a single thing, so that it's impossible to use the wrong behavior with the wrong data. So for example, let's say you were writing a weather predicting app, right? And it took in an array of integers that represented the maximum and minimum temperatures, maybe also things like the humidity and so on. And its job was just to spit out a prediction for tomorrow's weather. That's it. But let's say you also had a program for marking students, and it took in an array of integers that represented students' marks and their for their various assignments. If you accidentally sent weather data to the student marking app, that would be very bad, because it wouldn't know that these integers didn't mean something other than student marks. Likewise, if you send student marks to the weather app, it will give you happily a prediction for tomorrow's weather, but it won't know that that's meaningless that you gave it. So it's very nice if you can group all of the data and behavior for a particular entity together into a single unit, so that you can't do anything with that data that's not legal on that data. So for example, if you grouped all of the students' marks together into a marks object, you wouldn't be able to send a marks object off to the computer science, to the predict weather function. And in fact, what we actually do is we put the behavior inside the structure as well, the object as well. So you in fact wouldn't send the marks off to a calculation function, you would simply tell the marks to calculate. Say, for example, whether the student passes or fails. So the actual behavior is joined together with the data, which is a very useful concept. Secondly, we've got inheritance. So sometimes you've got things that are similar to each other, but with a few small differences. So for example, we've got students and we've got people. And there's stuff that's similar between students and people and stuff that's different. So we've got biographical details for a person, and maybe a person has an address, and maybe a person has all sorts of attributes that define them. And a student will have all of that stuff as well, but also a student number, and also the ability to do classes, and also the ability to register and deregister, and all of those other things. So inheritance lets us define new types based on their differences from existing types. So we only need to specify what makes a student different from a person, and it can still behave like a person in all of the situations where a person was necessary, but it now also has those extra things. We didn't have to redefine everything from scratch. And that's where it ties into this thing called polymorphism, because you'll often want different behaviors to occur depending on what type something is. So let's say, for example, you had an array of people, and some people are students, and some people are policemen, and some people are health workers, and they must all go about their day depending on what their type is. So the student must study, and the policeman must patrol, and the health worker must care for people, provide healthcare. But you don't want to know what something's type is in order to be able to tell it what to do. You just want to be able to tell it, go do your thing. And it must behave correctly based on its underlying type. So we will do that. We will specify for the students, for those behaviors that we want to behave specially according to their type, that they're polymorphic. And then the correct thing will happen when we use it, rather than us having to know, oh, this person is a nurse, have them perform healthcare. Oh, this person is a policemen, have them patrol. It can all just happen automatically. It's a very powerful technique. Inheritance and polymorphism were, in my opinion, the two techniques that were perhaps overused during object orientation's heyday, because they are the most powerful of the tools in the object-oriented toolbox. So there is the danger of overusing them where they're not supposed to be used. And we'll try and point out examples of where it might not be the best way of using them. And there are other techniques beyond these three, but these three are often considered to be central. So what is our goal in life? Our goal in life is to try and realize these different techniques and some of the other ones that we will see later. So we'll start off with encapsulation, the ability to join data and behavior into a single entity. So for that, we would like to the ability to group data together. We already have that. We have that inside structures. We can group all sorts of related data together. What we didn't have was the ability to group behavior with that data. So for that to work, we could perhaps try and use that thing we spoke about just a moment ago, the fact that a function is actually a place in memory where the compiled code for your function is stored. And if we get the address of that place in memory where the function is, we could store that along with the data. And that way we've unified the data and the behavior into a single entity. And that was the goal of encapsulation. And we'll see that this kind of works, but it's not perfect. It's awkward to use. Now, to be honest, several very important systems are written in an object-oriented way without using an object-oriented language. And the original C language that C++ evolved from was such a language. It never supported object orientation, whereas C++ does. In fact, that was the original reason for C++ to exist. It was originally called C with objects, and it was a bunch of preprocessor macros that automated some of the things that we'll learn how to do now, until it eventually became its own language. So, and there are projects, very important ones, like, for example, the Linux kernel, which are written in C, not C++, but they're written in an object-oriented style using, for example, structures and function pointers and so on, but without an object-oriented language like C++. So it is possible to design solutions in an object-oriented way without necessarily implementing them using an object-oriented language. But we will see that for our purposes, it's a bit awkward to work this way, even though it is technically possible. So what do we need to do? Well, we need to store the data in the structure. That's easy. But we also need to bind the structure so that it knows that its functions and data all belong together. So we actually need to add an extra parameter to every single one of these function pointers that tells us which of the many possible instances of this structure in memory that exist is the one I'm interested in. Because a function doesn't know what data is associated with it unless you pass that data as parameters. And if we had to pass all of the data members of the function as parameters to each of the member functions, that would defeat the point of grouping everything together inside a structure. So we basically make each of these function pointers take an additional parameter, which we're going to call self, which is of the type of the structure, but a pointer to it. So basically, where in memory can I find the rest of the data that's necessary for me? And we will see that C++ and all object-oriented programming languages, at least almost all conventional object-oriented programming languages, will do this for you in an automated way. And they'll typically call this extra parameter that they magically add for you, they'll call it this is the most common name. But self is also sometimes common. So we're going to call it self so it doesn't conflict with C++'s version of it, which is called this. And you'll then see in the future when you write object-oriented programs properly using proper classes that rather than just structures, you'll see that this exists and already has a correct value. And the reason for that is that it's serving this role of keeping these sets of data associated with this version of the generate function being called, let's say, from that structure. So you'll see it's a bit awkward to assemble. We have to, let's say we're making a function that's going to build a instance of this number generator structure, right? So this function, we'll call it construct. And also we'll see that in proper object-oriented programming using C++, there is a type of function called the constructor whose job is exactly this, to initialize and allocate the memory for your instances of the structure. So we're going to use that term quite a lot. The in-memory version of your type is called an instance. So your type, for example, would be student, and then all of the students that exist would be instances of that type. And if you've done that in an object-oriented style, we call the instances objects. That's just some terminology to use. But anyway, this function's job is to create a number generator with a certain length. So it locally creates a number generator pointer, allocates memory for it, just like we did in our game creation make world functions. It then sets the various parameters, except this one here, we're allocating everything on the heap, everything on the free store. So it's returning a pointer. So very importantly, if we want to set the length, we have to first dereference the structure, then dot. If we want to set the state array, we have to first dereference it, then dot, and allocate the memory for it. And if we want to set the function pointer to the address of some function, we have to dereference, then dot. And you can optionally also add an ampersand there. It doesn't make a difference. I typically will, but this generate even numbers is a function somewhere that will generate even numbers. So there is some implementation of a function associated with this function pointer that we can get to if we call the generate member of a number generator. And then likewise, we also need a function whose job it is to undo all of that, to deallocate the memory, so in this case to delete the array, and also to delete the function pointer itself and set it to null. Or in this case, we'd often use the null pointer C++11 macro, but this is trying to look as much like C as possible. Except for the keyword delete, we'd use malloc and free in proper C, but other than that, it's very C-like C++. So these two functions, the constructor, or the construction function in this case, and the destroy function, have equivalents in object orientation called constructors and destructors, which we will study in more detail. So I just want to show you one other little thing, which you'll see a lot. And it's just a notation difference. If you've got a structure, let's say a student, like we had earlier, right? But in this case, we have a student pointer. and we wanted to access their name. We could do like we did there, dereference the student dot name. Right? Or, and this is very, very common, because it's something you do so often, there's actually a much neater notation than the star and the dot together, and that's the arrow notation. So we can go S arrow name is equal to. So what this does is it's exactly the same. There's no difference. It's just, it's much easier to read. We've got a pointer here and we're accessing the member with the arrow rather than, over here's a star and then over here's the dot. This is easy enough because this is such a short term, but what if this were a very long expression with all sorts of things going on? Then part of the logic is over there and part of the logic is over there, and it can get confusing. Whereas if you use the arrow notation, it's always very clear that you're doing dereference and dot together at the same time. So just bear that in mind. That's you'll see a lot of that arrow operator, and it's exactly the same as dereference dot, but they always stick together like that, so it's never confusing as to what's going on. So that is something worth pointing out. I think I'm going to stop there because it's this technique that we're using at the moment. We're going to call it pseudo objects, because they're not really objects. They're basically our way of trying to fake object orientation without using the proper tools from C++. So this is how you would do object-oriented programming in something like C, but it does teach us about a lot of the important principles. So for example, we need a set of functions, at least one, that can create instances of the type for us, and they will allocate the memory and initialize everything and bind the functions to the function pointers. Likewise, we need a deallocation function, a destruction function, to deallocate the memory. And likewise, we need a special extra hidden automatically added member as a parameter, which will associate this version of the structure in memory with this particular call of the function, and we've called it self, but as you'll see in C++, it's the automatic one you get is called this. So the idea is that we will build up object-oriented programming ourselves from the ground up so that you can properly understand it, rather than just teach it to you without showing you where it comes from so it seems like magic. That's the basic idea. You'll only ever need to do this pseudo-object style of programming for one practical and in your first semester test. In practice, unless you do programming in something like the Linux kernel, you'll never really use it all that often, but it helps you understand why object-oriented programming works the way that it does. So that's that. So I'm going to leave us there. Actually, we're really right at the end, but that's fine. So we'll start off the next slide tomorrow. So this basically just covers what we said with the arrow operator, with why object-oriented programming isn't perfect, and the beginnings of the next thing afterwards, which is the proper use of classes. So our tutorials in this week will focus on implementing things using the pseudo-object style going forward. Okay, so thank you, ladies and gentlemen. That's that. If you have any questions, feel free to ask me on Discord or via email, and I will see you later. I think Mr. Satunga will be taking today's tutorial. All right, thank you. And we'll post notices for the archived versions of all of the slides, of all of the lectures and tutorials going forward. So keep checking Eve. Thanks. Bye.